Okay, so normally what I do, you know what I do. I'm going to start a program from scratch, and I'm not going to do that this time. I've already put together most of this program. So this is a calculation to show you how a velocity selector works. I will link a video describing the velocity selector down below, and you should look at that first. But the basic idea is to shoot a particle in a electric and a magnetic field, and if the velocity is just right, those two, the force from the magnetic field and the force from the electric field, will cancel and it'll go straight through. Okay, so let's just look at what I have right here. I've already made some stuff. Let me just show you the program and I'll show you the parts. They're tedious and boring and stuff like that, so I've already run this once. But here I have two plates, and then I have a little, that's a target area that I want the things to go through. So I have a lithium ion I start with over here. It's going to move this way, and then this is no force acting on it at all. And this is in 3D. So I also kind of put in here the electric field is down, and the magnetic field is to the right. Oh, it's into the page, really. Okay, so if you want to look at how I do this, and I'll give you the code. So here I just have some parameters that I would deal with. Here's my lithium ion. I made it a sphere. I made a top plate. I gave it a position, a bottom plate, and then the whole is a cylinder. Then these arrows are just arrows. I just picked some. They're just for show. Okay, that's not even cool. And then I have here the value of the electric and the magnetic field. I picked it to go along with the velocity of my particle, which I picked at 10 to the 6th meters per second. This is a tricky part that you have to play with right down here, the time step. If I have it's an ion going 10 to the 6 meters per second, then the step size and time are going to have to be really short. So I use 10 to the negative 9th. Okay, so now for the magic. While some amount of time, you could do while the particle is less than an x position, but then it might not get there. So I ran it once to get the time, and then I use this time. Remember this rate right here? This tells you how many calculations per second. So this will not do more than 100 loops per second. So you can see what happens. This is my force that I calculate. I start off with a 0 force. And then this is, so my particle, let me run this and you can kind of get a view for what's going on. So there's my lithium ion. I don't know why it looks like it slows down. I think that's optical illusion. And so at this point right here, I want the electric and magnetic forces to be on it, but not over here. So I start off with a 0 force. So then I just have to, once I calculate the force, whether it's 0 or something else, I just use that force to update the momentum. I did this also in the proton in a constant magnetic field program, and I went through all the details there, and I'll link that down below too. And I'm pointing, you can't even see right now, but I'm pointing down below to where the description is. The next thing is to update the position using the momentum and the time. And then these lines right here just say, okay, if it's going to hit a plate, then stop it. That's all that does. So let's start off like this. I'm going to say, let's just add the electric force. So the charge on the particle is, what did I put it? E. Okay, so it has a charge E. So I'm going to say the electric field, the electric force is going to be E times the big E, which I used for this electric field in the negative Y direction. So that's the only force I have on it. Let's just run that and see what happens in that case. Okay, so you see what's happening is that there's a electric field's down, it's a positive charge, and the charge gets pulled down. This is projectile motion because I have a constant force in the Y direction, and that's why I put the electric field down. It looks like projectile motion. It doesn't have the same acceleration, but it doesn't make it through. It hits down there. Okay, and let's just do this. What if I change this to a negative charge? So it's a negative ion. Now it's going to, the electric force is up, but it does the exact same thing. Okay, so let's make that back positive. Now let's add in the magnetic force. So the magnetic force is going to be equal to the cross product of Q, which I called E, times the velocity, which I need as a vector. So it's going to be Li dot P is the lithium momentum, divided by Li dot M is the velocity. I never actually calculate the velocity, so I'm just going to use momentum over mass for the velocity. And the B field, which I have up there too. So let's see what happens now. Oh, you know what? It didn't go straight. I forgot. I forgot. That's fine. I think that's good. Because actually what I did was I calculated the proper velocity. And then I increased the velocity to see what happened up here. I forgot it. I was playing around with it. So let's put this back at 1. And so this is the proper velocity. And it's going to go just straight through. Just like before. So the magnetic force is into the magnetic force is upwards, right? Because of the right-hand rule, if I have the velocity QV is this way and B is that way, that's going to make a magnetic force upwards. Remember the right-hand rule. Let's do this. How about this? Let's change the velocity, the magnitude of E. Actually, I need to do it up here. Let's just say E is negative, so it's an ion. What will happen? See, it still works. There's no deflection because the electric force is going to change direction, but so is the magnetic force. So everything's cool. So let's put that back the way it was. So now let's increase the velocity. What if it's 1.3 times the correct velocity? And you'll see what happens. And it just kind of hit that hole. You know, you can make that hole the whatever size you want it to. Let's make this go too slow now. 0.56. So 60% the correct speed. But then now, in this case, the magnetic force is going to decrease because it depends on the velocity. But the electric force is still the same. So my electric force is not going to be as much as my magnetic force. I'm going to be pulled down. And it stops here in the middle because I did a time-based loop. And it's starting slower, so it doesn't go as far. So that was just my fault. But you could see where it was going to go. So you can try changing them. Let's do that. Let's change the mass. Let's put this back at, let's put it at 0.9. Let's make this twice as massive. And it's going to deflect a little bit downwards because I picked a 0.9 velocity. But the mass doesn't matter, right? The mass doesn't matter because as long as those two forces cancel, then it will move along at a straight line. And in this case, there is a slight force, so there will be a downward change in momentum. And so the mass does matter if the forces don't cancel, but if they cancel, it doesn't matter. Okay, so I'm going to give you this code, and there's a whole bunch of things you can play with, but I just wanted to show it to you, see how you could model this. I was thinking about generating a whole bunch of particles over here with a normal distribution of velocities and see which ones make it through there, and that'd be kind of fun. But that makes it much more complicated. So I will save this, and I'll link to this code down below, and I'll talk to you people later, and we'll do some more physics.